It links to a lot of stuff, and you can learn a lot of stuff from it.
Okay.
And then, like in one of your papers, you talked about linking it to the ideal gas transition temperature.
Ideal gas transition temperature, yeah.
Yeah, and then if that's constant, I'll just write it down a second.
So,
Yeah, if that's constant. Oh no, so at T0, the material becomes non-conductive. That's what I've got.
that's I mean, that's to do with, not really to do with NMR, but that's to do with the definition of what an ideal glass transition temperature is. It's the temperature.
Oh, is it glass transition?
It's glass, yeah.
Oh,
You said gas, didn't you?
Yeah.
Yeah. It's,
Oh, it is gas as well.
yeah, I know you get ideal gases, don't you? So yes.
Yeah.
It's the temperature at which all the motion inside your system has stopped.
Yeah.
But it hasn't
Entropy goes.
Entropy goes to zero. But most students will say that, but they don't really know. Why do you say entropy goes to zero? Why does entropy go to zero? What's that mean? What?
So that means it's perfectly disordered?
In fact, quite the opposite. Because remember, entropy increases, doesn't it? And disorder increases. Yeah. So entropy zero is actually the lowest entropy. Zero. You can't. It has to be a positive value, so it can't be negative. So zero is the lowest number. So you've obviously. I mean, most students don't like entropy. I'm not sure if I really got my head fully around the concept of entropy. You learn about it in thermodynamics, don't you?
Yeah.
And the thing that makes it for me, or maybe for you too as well, confusing, is that you learn about it in sort of at least two distinct ways. Maybe your experience is different. The first way is through gases and thermodynamics, and you learn it as a state variable. So you learn about pressure, volume, temperature, energy, entropy. And you've got these equations which involve TDS equations. It was always a joke when I was learning TDS because they have T delta S's or TDS's in them, and it's like PV something something TDS and something, and there's a whole lot of thermodynamics.
Yeah.
Okay. So that's a kind of macroscopic way of describing things. A gas has a pressure. You don't care about the molecules or where they are, how fast they are. You just say it's got a pressure. This room has a pressure. And of course, the individual atoms don't have a pressure, or the individual molecules don't have a pressure. So it's a macroscopic property. The microscopic one, there isn't such a thing as pressure, if you see what I mean. Yeah. Same temperature, a molecule can't have a temperature, but a group of molecules, like in this room, the air in this room, they can have a temperature. See, and a molecule can't have an entropy, but a group of molecules in a room, they can have an entropy.
Yeah.
So you have these kind of what are called state variables, these macroscopic properties. That's one way of learning it. The other one is then people do statistical mechanics, and you do, you've got these atoms, they have these masses, they have these speeds, they have these positions, and you get into all the microscopic detail. And the genius is to connect all that microscopic detail to the macroscopic one. I mean, what is temperature? How does it relate to how they're moving? It turns out temperature tells you about the average kinetic energy of these molecules. And entropy is telling you about the order and arrangement and the number of available configurations that these atoms and molecules have. So the other way of learning entropy is then about the number of microstates, as I think they're called, that are available for a system. So if you have lots and lots of different ways you can configure yourself, then you have a very high entropy.
Yeah.
If there's only a couple of ways you can configure yourself, then you have a very low entropy. And then it's Boltzmann came up with there's a famous equation.
S equals K log omega.
K log omega, yeah, it's omega. So it's so entropy, S, this thing you've been measuring as a macroscopic thing like pressure, volume, temperature, entropy, all of a sudden he related to a microscopic thing, which is this omega, which is the number of available ways of arranging the system.
Statistical way, yeah.
Yeah, so S equals K log omega, and that's the same S. So that's on his grave actually, in Boltzmann's grave. You've probably seen it. It's quite a famous picture that people show this. There's a whole sad story about his death, I think, and people don't believe him.
He topped himself.
I think he committed suicide, as well.
But no one believed his theory. Was it?
I think all that thing, and now it's kind of the bedrock of kind of statistical thermal physics.
Yeah, Dr. Sarah Harris told us about it because she taught us statistical mechanics.
Yes,
so she told us at the start.
So yeah, so when you say the entropy is 0, what you're actually saying,
There's only one way to configure it.
yeah, and so omega is 1, and log of 1 is 0. So people talk very poetically that entropy vanishes. All they're saying in that kind of arty way of speaking is that the entropy's gone to 0. So yes, that's it. So there's just, what happens is the system locks up, and there is literally just one way the system can arrange itself the way it is right now. There's nothing else available to it. And that's what happens at this ideal glass transition temperature, is that it stops. And there's a whole lot of debate about, this is not my area of expertise, about whether a glass is actually really something or not. Is there really such a state as a glass? And what is a glass? What I mean by that is the entropy 0 or not? You see, there's a difference. Maybe a glass isn't what you think it is. Maybe there are millions of other states that are available, okay? But the time it takes to get between states is so slow, maybe it takes years to get between the states, that you as an observer go, it's got one state, and there it is, and that's it. You see, where maybe if you lived on a zillion year or a billion year timescale, you would say, no, that's not a glass, that's a liquid, because it's moving between all these states. It just takes a million years to move between states. I live a billion years, so it doesn't matter, you see. And so there's an argument of whether a glass is really, locked up, or is it just very slow? How would you know?
How would you know? Yeah.
And so on. So, and that's not my area of expertise. So yeah, and you get all these. There's a problem. There's confusion because people muddy the waters a little bit because there's a bit of misinformation that goes around. For example, often the flowing of glass windows in churches is used as an example to show you that the glass isn't fixed, that it flows. Have you heard that? About how glass, if you go to an old church, like 1,000-year-old church, you can find many of these in the UK. The glass panes that have been sitting there for like 1,000-odd years, they're thicker at the bottom than they are at the top. And so people go, oh look, the glass has flowed over 1,000 years. Have you heard that said ever?
No, I've not heard that said. No.
Yeah, no. No. It's not true. That's the glass is thicker at the base, but that's not because it's flowed over that time. It's because that's how it was made and manufactured. The reason for that was to help set it up. It gives it a bit of stability at the bottom, so you can put the piece into the window frame. So it's not the flowing there.
It's just a rumour.
Well, yeah, it's just people have noticed that glass is thick at the bottom. They go, oh, it takes over 1,000 years. It's flowed. Look here, we can see it. No, it's not what's happened. It's actually made that way.
Yeah.
But there's a lovely experiment. I've ever told you before. There's the world's longest, the world's longest running experiment, man-made set-up experiment, is actually in Queensland, Australia. But the second longest running experiment in the world is in Glasgow. Was set up by Kelvin, as in the temperature scale, Kelvin. And he put, it's the same. It's very similar to the Queensland one. He put a piece of ebonite. Ebonite, if I showed you a piece of ebonite, it looks like a black, very dark glass.
Right.
And you could look at it all day, and it's clearly a lump of solid glass. And if I asked you whether it was a liquid or solid, you would clearly tell me it's a solid, okay? But on the timescales of decades to hundreds of years, it flows. You see, so and that's not a myth, it does flow. And so what he did, he set up, he put a piece of glass about the size of this table, about the thickness of this table, roughly about this size. You can go and see it. And so when Kelvin existed, he took some lead bullets and put them on top of this glass. And he took some corks, like from a champagne bottle, and put them underneath, like that. Got it? And then over the 100-odd years or so, the lead bullets have started to sink through the glass, and the corks have come to the top. So,
wow.
So it's as if it's a liquid, but just really, 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 really slow. That's it. There you go. Okay, so yes, that's the ideal glass transition temperature.
Yeah, and then you could also work out like how your relaxation time depends on salt concentration. Yeah. And then there's also a use of high energy density batteries. Yeah. So you can just see how that relates to the segmental mobility of the polymer.
So for conductivity, you probably, and I say probably just in case, need mobility of the polymers themselves. Though that's argued. That's why I said probably.
I really just glanced over all the entangled stuff. I just kept it to what I could figure out.
Cool. Yeah. So that's you've got all that. So what's the advantage then? Here's a question. What's the advantage of these polymer electrolytes over traditional liquid electrolytes. Traditionally, people have used liquid electrolytes in batteries. What's the advantage? Why would you want to change? Who cares? That kind of thing. Can you think of it? Do you know, or did you read or hear about one advantage even?
It's got high energy density.
Yeah.
You can pack more in small
I don't know
space.
if are they as high as liquid batteries? I'm not sure if they are. I don't know. I have to check that.
Maybe they're rechargeable. I'm not too sure.
Liquid electrolytes, these are rechargeable. Then most, if you buy, you can buy rechargeable batteries, can't you? Like AA batteries that you can recharge. I think they're just liquid electrolytes, so you just recharge. So, all right. Well, there's a good question for you. What is the advantage of a solid electrolyte over a liquid electrolyte? Why would you care? Why would you give me? What's one advantage?
Would you like us to look that up, or do you?
Yeah, go on. Let's find that out. Yeah. Okay. Did you ask yourself any interesting questions? Did you, That was remember that was the challenge of the research, was to ask yourself interesting questions and try and answer them. Didn't you also say you were going to use lab books, or was that somebody else?
Yeah. I like to write it. Like my writing's awful.
That's okay.
I
think I did say that I don't care about your writing.
Like, it has no structure.
Okay. A lab book should literally be, not literally, I mean, should actually just be a diary of what you do. So all these thoughts, all these scribbles, all this lack of structure that you're worried about, there it is.
I thought I'd put it all in, just a bit neat.
No, that's not what a lab book is. What we're trying to do is this is meant to be training in part for either doing a PhD or for working in research, in maybe working for IBM or something in a lab or something.
Yeah.
You don't think in the real world you have time to work live and then later copy it up. You just do the work and there's the record of it. So, and that's it, that's your live notes they are. And so people can say, what did you, if you work for IBM, what did you do on January the 14th? You go, on January the 14th I did this.
Yeah.
Look at all the stuff I did, and it's scribbly no size, but that's what you did. Or, people say, well, can you check how you made these measurements? Because we're now doubting them. They seem to contradict other measurements. Then you can go back in your notes and you can look at all how I set it up, how I did all the measurements, and you can say, they go, oh yes, but you didn't do that. And you go, oh gosh, no, I didn't do that. No, that's probably why they're different. And it's all there recorded, as is, you see.
Yeah.
What you're mistaking, what you're confusing, you see, this is a bit of a, if somebody asks you to write a report, then they're asking for what is in effect an executive summary, which is then a neatened version of your lab book, where you've gone through your lab book and gone, oh yes, we did these measurements and carried out, and you put a much more easy to follow and logic and neat. So somebody who is employing you can read it and go, oh yes, Bert, he did the measurements on the whatever, and these were the results, these are the main conclusions, these were the challenges. It's got an executive summary. You won't look at your lab book for that,
Oh,
but your lab book isn't the neat executive summary. It is actually the live day-to-day work, from your research to your measurements to your everything.
Yeah, that's right in the lab book then. Yeah.
Cool. Yeah, it's ditto, because you're just using a notepad like that. Yeah, so you should just use your lab book. Okay, cool. Anything else? You got any questions? You got any worries? Do you know what you're doing next? This is for you, by the way. It's not for me. This hour. It won't be an hour. This amount of time. It's for you, so that you know what you're doing. You're happy. You know what you're doing next.
Honestly, it seems pretty straightforward for all the data, getting all the data.
Okay.
I think next week we'll have more questions when it comes to analysing what you actually want us to do with the data.
Okay. Remember that we said there could be overlap, is that when you're doing measurements you can also start analysis. It doesn't have to be, as soon as you've got numbers, as soon as you've got some numbers, you can start to play, start to do something.
Yeah.
Because what you don't want to do in life is work in series. You want to work in parallel. You don't wait until you meet the problem and then get stuck. You're doing the measurements, and you're doing the analysis. So if I get stuck here, I can continue over here, or you can anticipate getting stuck. And while you've still got something else to do, you can talk about this problem over here. If you wait until you get a problem, you just stop dead and you've got a problem. So, have you?
So really, you want us to get a graph like this?
Against what's F?
Frequency.
Oh yeah, typically it's R1 is the way to present it, so it's the other way around, it's the traditional way. So R1 is...
That's just what...
That is R1, yes, yeah, you're right. Sorry, me being pedantic, no, correct. So R1 is 102, so you plot R1 against frequency. They traditionally look more like that, but that, yes, doesn't matter.
Right, yeah.
Against frequency, yes.
So how do you show at different temperatures?
Well, it's up to you. There's different ways of showing things. You see, you can either... Well, this is exactly what you've done. These are different temperatures.
Oh, I
Yeah.
thought these would be different, different
The molecular weights.
molecular
Well, they could be,
weights.
yeah. You can't put it all on the same graph. There's
Oh, so you have to do it